Hi everyone, I'm Fanchen, a PhD student at KAIST. Today I will introduce our work titled Age Probability Graph Models Beyond Age Independency, a joint work by KAIST and USC. So this work is about random graph models. First of all, what is random graph models? Random here doesn't mean arbitrary. Instead, random graph models are designed to reproduce real-world patterns. Good RGMs should not only reproduce real-world patterns, but it should also be variable. They generate not too similar graphs, and they should be tractable. We should be able to compute and control the graph statistics of the generated random graphs. So one metaphor is random graphs are like zero Coke, and the real world ones are like real Coke. So zero Coke should taste like real Coke so that we can use them as substitutes when we have some practical concerns, for example, for our health. Specifically, RGMs have all these real-world applications that have shown its usefulness. So here are some classical examples of RGMs. We can see that those different RGMs, you need to give different informations to define them, and they can reproduce different patterns. But one common point of all these classical ones is that age existence are determined independently to each other. Therefore, you can see the figure, each age has its own dice and it's determined by the dice. So people call all such models age-independent graph models, and we can see that all these classical examples fall into this category. Then we can imagine that there must be some merits, and actually it's true. Such models are simple and they are mathematically concise and elegant. But they are not perfect. Their merits come with cost too. So the limitations of age-independent graph models have been discussed by previous works. One of the most notable one, which we also focus on in our work, is the inevitable trade-off between variability and the ability to generate random graphs with enough triangles. And that is, if we want high triangle density, you must sacrifice variability. Okay, how can we improve this? Specifically, we want to keep the merits of those models and improve the limitations on triangle density. So we first provide a novel perspective of random graph models. Each RGM is essentially a distribution on graphs, which is mathematically a multivariate distribution on edges, which can be further decomposed into marginal age probabilities plus the dependency between them. We can see that the merits of age-independent models mainly come from their well-defined marginal age probabilities, and their limitations are mainly because of the age independence. Therefore, with this novel perspective, we have the idea that we can keep the marginal age probabilities while introducing age dependency. And based on this idea, we propose the concept of age probability graph models. EPGMs are defined on marginal probabilities of all the node pairs. For simplicity, here we assume nodes are labeled with positive integers from 1 to n, and the marginal probability of each age is given in this variable p. Then the set of EPGMs with regard to p consists of all the random graph models that satisfy the marginal properties given in p. Then all such EPGMs share the same marginal age probability p, but they vary regarding the age dependency. Here we show some examples with marginal probability p in the left table, and we have three different RGMs 1, 2, 3, all satisfying this p. So we can examine the correctness by looking at each node pair. Here for the pair between the node 1 and 2, its marginal probability is 1 over 2. Then we find all the possible graphs where the age between 1 and 2 exists, which are G2, G5, G6, and G8. Then we should have the sum of probabilities of those graphs equals to the marginal probability, and then we can say this marginal probability is preserved. Here, by some simple calculations, we can see that the marginal probability is preserved in all three RGMs. And we can do the same validation for the other two pairs. Okay, note that here we wrote down that RGM1 is age independent, and you can validate that by calculation. And RGM2 and 3, they are dependent, but the extent of dependency is different. We will talk more about this later, but intuitively, for RGMs that are more dependent, you can see the probabilities are more concentrated on a few possible graphs. And note that here are just 3 examples. We have infinitely many ways to construct RGMs satisfying P as long as the marginal probabilities are preserved. Now let's talk about some basic properties of the proposed concept EPGMs. First, we can see that any RGM can be decomposed into marginal probabilities and dependency. Therefore, any RGM can be represented as an EPGM with regard to its marginal probabilities P. That is, EPGMs are mathematically general. Also, recall the main limitation of age-independent graph models, which is if you want high triangle density, you must sacrifice variability. However, for EPGMs, you can keep the same marginal probabilities P, and therefore you keep the same variability, but it's possible to have more triangles by introducing age dependency. Let's revisit the examples we showed previously. As mentioned, those 3 RGMs have the same marginal age probabilities, and therefore they have the same variability, but as we can see, they can generate different triangle density, which is the probability of G8. Okay, to summarize, EPGMs are mathematically general, being able to represent any RGM. They are variable. Each EPGM has the same variability as the corresponding age-independent model with the same marginal age properties. While being variable, EPGMs break the limitation of age-independent models, having the potential to generate more triangles. With that in mind, let us revisit what we want for good random graph models. First, for real-world patterns, EPGMs do better by being able to generate more triangles. And the second one is done without sacrificing variability. So the remaining main question is, are EPGMs mathematically tractable so that we can compute and control graph statistics of the generated random graphs? Let's recall one properties of EPGMs. That is, they are general, being able to represent all possible RGMs. But at the same time, this is also a shortcoming because they are too general in the sense that without additional conditions, we need to consider all possible RGMs, which is definitely not mathematically tractable. So in this work, we try to study EPGMs with these research questions from both theoretical and practical perspectives. For theory, since EPGMs are too general, we need to add some constraints to reduce our scope to some subsets of EPGMs, but we don't want just arbitrary subsets. We want those subsets to be good in the sense that they should be realistic, flexible, and tractable. And for practice, we also need efficient algorithms for both parameter fitting and graph generation. Let's first find good subsets. For this, we propose binding, a systematic framework for imposing age dependency. The high-level idea is to group node pairs together and decide those pairs in the same group together. By doing this, we introduce dependency among the pairs in the same group. As illustrated below, instead of rolling a dice for each age, we roll a single dice for all 3 ages. We shall show that our binding framework can get good subsets with the 3 desirable properties discussed before. We will revisit our examples again, and we will see how those three RGMs are actually examples of binding. As mentioned, RGM1 is just age independent. In other words, each pair is grouped alone. For RGM2, actually the two pairs 1, 2 and 1, 3 are grouped together. Specifically, this means that we sample a single random number S between 0 and 1 for both pairs in that group, and the two pairs are determined with the same number S. Look at this specific computation here. When S is small and both P12 and P13 are above S, then both of them exist. And then when S increases to between P13 and P12, the pair with higher probability exists, which is 1, 2. And when S is even higher and above both P12 and P13, both pairs don't exist. For RGM3, all three pairs are grouped together with a single random number S. Here is the detailed computation in a similar manner. The idea is that when we group pairs together, when we look at each pair, its marginal property is preserved, but by using the same S for all pairs in that group, we impose age dependency. Intuitively, when more pairs are grouped together, we have stronger age dependency and consequently more triangles. Maximally, like RGM3 we just saw, all the pairs are grouped together and determined by a single number S. Minimally, we group nothing, that is the original age-independent models. Between those two extreme cases, we have a whole spectrum of binding. However, as we just saw, we have many different ways to group pairs, and actually many of them are not that meaningful. For example, we may not want to group irrelevant pairs that are far from each other in the graph. To this end, we propose to use node-oriented grouping. That is, we first group nodes, then bind the pairs between them. A good thing is that such a way of grouping is realistic. It mimics the way of how real-world graph interactions are formed, where multiple people form a group and the interaction between the group members depend on each other. Instead of specifying a specific grouping, we propose an iterative, probabilistic framework to group nodes. So we keep sampling nodes, group pairs between them, until all the pairs are grouped. Here, let's see an example. In each round, we first sample nodes. We sample one by one and add them into the set of sampled nodes. We can see that each node is included in the set independently with probability given by the variable g. Okay, after sampling the nodes, we collect the pairs between them and group them. Then we sample a single random number S for the whole group. Then we check the pairs one by one and see which ages need to be generated. So each age is generated if its probability P is above the random number S. Then one round is over. We repeat this. First sample nodes, then collect pairs between them, sample the random number is, find the edges need to be generated, and finish the round. After all pairs are determined, either generated or perished, the whole process is terminated. We have just introduced the algorithm. Now we talk about the mathematical tractability of our binding algorithm. Specifically, we can compute the closed form expected number of triangles in a random graph generated with the local binding algorithm we just described. By linearity of expectation, we only need to compute the probability of each triangle. Then we can sum up the probabilities of all those triangles to get the expected number of triangles. One important fact is that for each triangle, the probability of forming a triangle only depends on how the three node pairs in that triangle are grouped. Let's revisit the examples where we see different ways of grouping the pairs give different triangle probability. So we only need to analyze each possible way of grouping, and then we can sum up the probability of each possible grouping multiplied by the probability of a triangle under that grouping. Due to time limit, we skip the detailed calculation here. One notable limitation of local binding is that it is non-trivial to parallelize it due to its temporal dependency, which means in one round, which an edge is generated depends on whether it's grouped before or not. So to this end, we propose a parallel version of binding, which is easier to parallelize. The key idea is to have temporally independent rounds, and the idea is basically each edge is possible to be generated in each round, and when we have the accumulated probability over all the rounds, you get back to the original given probability P. So here you can see one big dice is decomposed into 4 small dices in 4 rounds. And when they sum up, it becomes the original probability P. So we have 2 variants of binding, and both variants give ICDMs. That is, they preserve marginal edge probabilities and they impose edge dependency. At the same time, they are mathematically different, and we don't want to claim which one is absolutely better, but we do recommend the parallel version if you care much about efficiency. For binding, we have 3 main parameters: the edge probabilities P, the node sampling probabilities G, and the number of rounds R. For P, we assume they are obtained from some edge probability model, such as Erdos-Renyi or Kijung, and we manually set R. So the only thing we need to fit is G, and we use the expected number of triangles for which we have derived theoretical results as the objective of fitting. So why do we care about this number of triangles? The key idea is to keep the merits of edge-independent models and focus on improving their limitations, especially about triangle density. Now let's talk about the experiments. We use real-world graphs from different domains, and we care about their clustering metrics. So for each real-world graph, we first fit different edge probability models to get the P. Then we fit the G to match the expected number of triangles, as we mentioned. Then we generate using the same P but different edge dependency, namely edge-independent, local binding, and parallel binding. First, we show that with binding, we inherit the merits of edge-independent models. That is, we are also being able to generate realistic degree and distance distributions. We also truly break the limitations of edge-independent models, being able to generate realistic clustering levels with regard to all 3 clustering metrics. Moreover, we also improve with regard to other graph metrics. Here the values are averaged over all the datasets with the relative error of edge-independent models normalized as reference 1. So here, the relative error lower the better, and we can see that with binding, the error is much lower than the edge-independent models. So to conclude in this work, we have new concepts, we have a binding framework, we have theoretical results, and we have algorithms for both parameter fitting and graph generation. So for more details, including appendix, code, and datasets, you can visit this link to our GitHub repo. Thank you for your attention.